So there's some very interesting observation to be made, okay, and I'll tell you what they are. So the first thing is, okay, the first thing is when the shear force magnitude shear force magnitude is related to the gradient of the bending moment. Diagram. Okay. So let me elaborate. Okay. So if I'm going to divide this into ranges, okay, I'm going to divide this into range. And some of you might say, Eugene, this diagram is not messy enough. It is messy. So if I divide this, okay, so this is one divide. Then I'm going to divide over here. So the statement I make, okay, the shear force magnitude is related to the gradient of the bending moment. If you look at the magnitude over here, so M for magnitude, right? Magnitude is negative, right? The gradient is also negative, right? So the gradient positive has to go the other way, okay? The magnitude over here now is positive, right? So if you look at, if I draw tangent line, right? The gradient is also positive. Over here, after L/2, the magnitude now is negative. The gradient of the slope is also what? Negative. Over here, when the magnitude is positive, the gradient here is also positive. So you can see that the shear force magnitude is related to the gradient of the bending moment. Okay. The next thing I want to highlight is this. Okay. The next correlation you can see is this. Okay. The next correlation that you could see is when, yeah, the next correlation is this, when shear force is equal to 0, and I'll highlight this. Okay, there is a possibility that bending moment is at its maximum. Okay, so in our, that's why I picked this example. Okay, in our diagram, okay, the shear force intersect 0 at 3 points: at point B, at L/2, and at L minus A at point C, right? So we have to check, right? So when it crosses at point B, it's not as is at its minimum, not necessarily maximum. Why do you want to know minimum? So it's at this point over here, is at its what? Maximum, which we found is equal to minus omega L squared over 8 minus PA minus omega L over 2, so on and so forth. Okay. Okay. So that's where I mentioned this, that there is a what? Possibility. So you have to check, or everyone have to check, okay, that the when the shear force is 0, bending moment is at its what? Maximum. Okay. So what else do I, let me see, what else do I need to highlight between the shear force and bending moment diagram? Okay, so you can also see that when there is point load, okay, point load only, the shear force is constant or has no gradient, right? Means zero slope. Bending moment has a gradient. Okay, as you can see over here, right? I'm going to highlight from A to B, there's only point load, right? And the bending moment is a what? It's a slope. Okay. Then the next thing is when there's distributed load, right? Shear force has a linear gradient, right? And bending moment is non-linear. Okay. So you can see over here in between B to C, you have a distributed load, right? Linear. Over here, the gradient, okay? The bending moment is non-linear. It's a parabolic, as you can see down here. So these are the things that could help you, right, in your later courses, right, to construct shear force and bending moment diagram. I'm more concerned about later courses when you take, okay? Now, the next thing that I want to highlight down here, which I think is important, is once we have all these equation, okay, once we have all these equation over here, okay, the next thing is how to select a beam. Right? We have all this expression down here already, is how to select a beam. Okay, how to select a beam. Okay, how to select the beam. Okay, so the only way to do this, okay, the only way to do this is you have to know, okay, which area is the most critical. Okay, so now before we do anything, right, I'm going to select, I'm going to put some constant, okay, right, because all over here we are working on is all on variables. Okay, so we're going to put some constant, so we're going to put P, okay, P. So the point load that we have specified in the same example is 10 times 10 to the power 3 Newton. Okay, the length is equal to 45 times 10 to the power 3. Not fifth. No, what am I? The length is 15 meters. Sorry. The omega, the distributed load, is 45 times 10 to the power 3 meters, Newton per meter. And A is equal to 3 Newton per meter. And A is going to be 3 meters. Okay. Okay. So let me copy the example again. The diagram, this diagram. Okay. So now we have put in numbers. Okay. So we know that the distance from here to here is A. The distance from here to here is L minus 2A. The distance from here to here. So A we know is 3 meters, right? 3 meters. So this will be equal to what? 9 meters. The distributed load is 45 times 10 to the power 3. And the P is 70 times 10 to the power 3 each side. Okay. So now how to select the sizing of the beam? Okay. So there are 2 points that we have to check. Okay. There are 2 points that we have to check. So where the beam fail, it can fail at, depending on the load. Okay. Depending on the load, it can fail at point B. Okay. So this is where we have to check. Okay. We can fail at either point B. Why point B? Because there's a possibility that it has the very high what? Very high shear force, right? Or it can fail at L over 2 because it has the highest bending moment. No doubt shear force is equal to 0. Okay, so we have to check. Okay, we have to check which is higher. Okay, so we have to check. But sometimes, okay, wait, I'm not going to too much depth over here because we don't have time. Okay, but sometimes we can base the analysis, not always. Sometimes we can base the analysis on purely bending moment. Okay, so I'm going to teach you one method. Okay, so based on bending moment criteria. Okay, so based on bending moment, okay, based on bending moment, okay, we can have this expression. So the expression is stress max is equal to mx, maximum moment, okay, divided by second moment of area multiplied by c. Okay, so you guys see this, this looks familiar, right? So I is the second moment of area, and c is the furthest distance from the centroid. Okay, so I'm going to introduce a new term, is where we're going to let S, okay, is equal to I over C. Okay, so if everything is in meters, this the unit, right? The unit is in meter cube. Okay, so I'm going to introduce you to this term S. Okay, so stress max is equal to M max over S. Okay. So S